All right, in this section, 5.3, we're going to talk about graphs of polynomials. The first thing I want to talk about is some characteristics of the graph. A polynomial is defined for all x, and they're continuous. But what that means is if you draw the graph of a polynomial, it's always going to go from one end of the real number line to the other. You're never going to have any vertical asymptotes. You're not going to have any horizontal asymptotes either. And the continuous part says that you're never going to have a break in the graph like this, where you have the graph and it does something like that. That's not going to happen. They're continuous. They're smooth. Smooth means you don't have any kinks or corners. You know, one of the functions that we know that has a corner on it is the absolute value function. It's got a corner there, but polynomials will never have that. The other thing is, for degree 0 and 1, they're straight lines because, you know, degree 1 is linear. Degree 0 would be something like a polynomial y equals 4. Technically, that's a polynomial, and it has a very boring graph. It's just a horizontal line. But if the degree is greater than 1, so for degree 2 and up, they're always curved everywhere. So, you know, like a cubic polynomial might look like this. But you'd never have a polynomial that has a mix of straight lines and curves. You'd never have, say, a bit in the middle that's a straight line and then it starts curving over here. That won't happen. All right, so let's look at multiplicities and zeros. I want to do a few definitions. Then we'll look through this some of this stuff, but then we'll just jump to some examples because I think examples are a better way to get some of these ideas across. A zero of f of x is a number a for which f of a is equal to 0. Now that's true for any function, not just a polynomial. But this next thing here applies to polynomials. If a is a 0 of f of x, then f of x can be factored into f of x equals x minus that 0 times g of x, where g of x is a polynomial with degree 1 less than f. And this is Veronica, and she's trying to help me teach my classes today. All right, hop down. All right, one thing that's kind of interesting here, it says if this is a 0, then you can factor x minus a out. So I'm going to zoom in here and do an example. Let's say we have the polynomial f of x. Let me make this a little smaller. F of x is equal to 3x squared minus 7x minus 20. And let's say that we're just told that 4 is a 0. Somebody just gives us that information. We can verify it by doing f of 4. Well, let's see, if we do f of 4, 4 squared is 16 times 3 is 48. Minus 28 minus 20, sure enough, is 0. Now that tells us that we can factor x minus 4 out of this. So I could rewrite f of x as x minus 4 times something. And that's going to make factoring this thing really easy. Because in order to get 3x squared minus 7x minus 20, 3x is going to have to be multiplied by, x is going to have to be multiplied by 3x to get 3x squared. And negative 4 has to be multiplied by positive 5 to get 20. So we can factor this thing like that. In calculus, that is a useful thing. Given a 0, being able to factor the polynomial. All right. This next part I want to skip for a second. And the other part, instead of going through those, let's do this example, and then I'm going to come back up and talk about it. This example says it doesn't say, but we want to find the zeros of this polynomial. Well, we're given the graph, but the way you'd find the zeros is you'd set the polynomial equal to 0 and solve. Now, since this one's already factored for us, it's really easy. We can just set each one of these bits equal to 0. When I say it's easy, I mean we don't have to do the factoring ourselves. We still have to do the rest of the work. So this gives me 0. This gives me 2 for a solution, and this gives me -1. Those are my zeros. And the multiplicities come straight from these exponents here. So the multiplicities are 3, 2, and 1. Now, the multiplicities tell us a couple of things about the graph's behavior near those zeros. Over here, if we look at the 3 zeros, they occur here at x equals -1, x equals 0, and x equals 2. Now, whenever you have, this is where the stuff above is going to come into play. Whenever the multiplicity is odd, you're going to cross the axis. That happens here. We cross the axis here because this multiplicity is 1. And we also cross the x-axis here at 0, and that one had a multiplicity of 3. So whenever you have odd multiplicity, the graph is going to cross the axis at that 0. Now if you have even multiplicity, the graph is going to touch the axis there, but not cross. It's going to touch and turn away. And that's what happens over here at this one. The multiplicity is 2, and it touches and turns away. The other thing is, the larger the multiplicity is, the flatter the graph is at that 0. And you can see that here. This has a multiplicity of 1, and this has a multiplicity of 3. The multiplicity of 1, it just shoots straight through. Multiplicity of 3, it flattens out. And let's look at Desmos, because I want to look at something with some higher multiplicities. Let's say we had y equals x minus 2 and times x plus 4. So we've got a parabola there. Right now we've got 2 zeros of multiplicity 1. If I change this x plus 4, let's raise that to the 3rd power. That flattens the graph out at the 0, -4. If I start raising this to higher and higher odd powers, the bigger the power, the flatter it gets. Now, just looking at this graph, it kind of looks like a straight line in there, which goes against what I said before, but it's not really a straight line. If you zoom way in on it, there's some curve to it. Right here, it's curving down, and over here, it's still curving down. It's saying 0 there for all these y values, but that's round-off error. It's really curved, but it's very flat at that point. Let's put this back to something small. Let's say cubed. Well, let's just leave it as 1. Now, if I raise this to an even power, if I put a 2 there, it touches and turns now at 4. And notice it looks pretty much like a parabola right there because of that 2. If I change the 2 to a 4, or a 6, or an 8, the bigger that number gets, the flatter it gets at that point. If I make it to the 100, it looks like straight lines. But in actuality, those are just very severely curved. If you were to come over here to and trace along, it grows very fast. Doesn't look like it's growing very fast, but it's because I'm not moving very much. But anyway, that's how multiplicity affects the shape of the graph. All right, I've got 4 examples here. Let me actually put those on screen for you. This right here says list the zeros and their multiplicities of the following polynomials and tell if their graph crosses or touches and turns away at each 0. So I've got 4 examples here, and the level of difficulty of them varies. The first one is the easiest of the four. This one, A, has a 0 of, we get -2, and its multiplicity is 2. And then we get this gives us a 0 of 1, and its multiplicity is 4. So multiplicity of both of these are even, so these touch. Tell you what, I'm going to put, so I'm going to do all these examples. I'm going to put T for turn, meaning touch and turn. I'll put C for cross. All right, B over here. Now on B, we've got to factor it ourselves. Now, this is a 4th degree polynomial, but it's not too bad because we can factor it into x squared times 2x squared plus 3x minus 5. And I think I can further factor that into, let's see, 2x and x. I'm going to make this a little bigger so I can write a little better. 2x and x, and the 5 has to be 5 and 1. If I put the, let's see, if I put the 5 here and the 1 there, when I multiply it out, I'll get, that'll be, well, 2x squared, but that'll be 2x, and that's 5x. So if I make it 5x minus 2x, that will, that'll work. So my zeros here, I'm going to do the same thing. 0, multiplicity, and then touch cross. My zeros are 0. 2x plus 5 gives me minus 5 halves. This gives me 1. The multiplicities are 2, 1, and 1. And so that's going to touch, cross, cross. All right. If we wanted to, we could graph these on Desmos and check them, but no need to. Okay, this one. Let's factor this guy. It'll factor, this is, I'm going to call this part C. I did my cut and paste and I didn't change the names. But let's see, we can factor out x squared, and we're left with x squared minus 1. And so now I can factor that into x squared times x minus 1 times x plus 1. And we're home free. This is, the answers are the same as before. Zeros, multiplicities, and then touch cross. We get 0 with multiplicity of 2. So it touches and turns. 1 with the multiplicity of 1, so it crosses. Then -1 with the multiplicity of 1, so that's going to cross as well. Okay, now this other one is interesting. Let's call this D. It's already factored as much as it can be. This is going to give me a 0 of -3, but this is not going to give me any zeros. Reason being, x squared plus 1, if you set it equal to 0, you can't factor that, and if you try to move the 1 to the other side, you get -1. X squared is -1, so there's no real solution. So x plus 3 gives us this. The multiplicity is 1, and it's going to touch there. Now, what's going on with this? Why is this not giving us a 0? Well, if you look at it, if you multiply this out, you get an x cubed term. This is a cubic polynomial with only 1 0. We could graph it if we wanted to, and what it would look like would be something like this. I'm not going to actually graph it, but it would look something kind of like that. Well, my tablet just changed that into a straight line, but it's going to look something like that. And the axis is going to be down here somewhere. So it's going to cross the axis at -3. And that's the only place it's going to cross. All right, so I think we'll stop here.